Maybe I'll just use this time to introduce Ashvin. So, well, it's really a great pleasure for us to host Ashvin Vishwanath. Ashvin did his PhD at Princeton, working with Duncan Haldane, and then he was a Pappalardo Fellow at MIT. And after that, he became faculty at the University of California, Berkeley, where he was for a few years. And over the last maybe 4 or 5 years, he's been at Harvard. Now, Ashwin has many accolades, which include a Guggenheim Fellowship, and also he was a recipient of the Europhysics Prize. And well, I had a great pleasure on a personal note of having done a postdoc with Ashvin. He's already left a mark on Israeli physics, because he has at least 3 people who he's supervised who are now faculty members in different institutions in Israel. So, and today he'll tell us about emergent gauge fields and topology quantum matter.
Okay, thank you, Daniel, for that very nice introduction. So indeed, as Daniel says, I have, by now quite strong ties to the Israeli condensed matter physics community. In fact, I think 2 of the organizers are, my former collaborators, and yeah, some of my, best memories of doing science have been with people who are now in part of the faculty at Israel. So I'm hoping we'll be able to resume travel and get back to our normal life of collaborations. But I think till then, this is a great idea. You can bring together communities that are not that easily brought together and physically. Yeah, I'm hoping to hear people's reactions from different areas. I'll tell you what I'm most excited now. Maybe that's not the best choice for a colloquium, but it will tie into some general themes that I think have been developing over the last, maybe even a couple of decades in condensed matter physics. And I'll try to illustrate those themes with a couple of examples, which are from my own recent research, but hopefully, it'll be understood that those things are provisional, and we have to do a lot more work to establish that. Okay, so the main theme of my talk is about topology in quantum matter, and how this is reflected in technically in the form of emergent gauge fields. So gauge fields that we are normally used to dealing with in electromagnetism or in high energy models of particle physics and so on. They also have a life, and increasingly so in condensed matter physics. The examples I'll talk about kind of invoke that in a very significant way. Okay, so this work was part of the Simon's collaboration on what we call ultra quantum matter, but I'll try to explain what that means as we go along. Okay, so before I get into the meat of the talk, let me tell you how we used to think about condensed matter physics for the longest time. And in fact, even now, this is predominantly the way in which we approach trying to describe condensed matter systems. In particular, I'll be interested in quantum systems. So imagine that you're cooling the system down to very low temperatures. So you're really interested in the sort of competition between quantum fluctuations and ordering tendencies, or things that try to make the system classical. You get many different states of matter that qualify as a 0 temperature quantum phase. Some of them are quite conventional, like solids, ferromagnets. Some of them are a bit more exotic, superfluids. They've been known for a long time. There are others that are conjectured, like quantum spin liquids. All of them are described from the theorist's point of view by very universal properties. They're highly constrained. You can't simply assign any property you like to a phase of matter. The underpinning of all of this from the theoretical point of view is the idea of an RG fixed point. So quantum phases are really RG renormalization group fixed points, and that gives them a certain rigidity and certain strong constraints that have to be satisfied. Okay, so for the longest time, it was believed that all the different kinds of phases of matter that we have, the thing that distinguishes them is really symmetry. You have an underlying symmetry, and you can break it in different ways. And the low temperature physics, is associated with a broken symmetry, or that's captured by this Landau order parameter. That point of view has had enormous success. So to just quickly list what that point of view has done, probably familiar to many people. To quickly list that, so you can describe these states of matter by an order parameter. And for example, a ferromagnet, you capture the breaking of rotation symmetry, which direction the spins are pointing, by a vector order parameter. Okay? And that's established at low temperatures. For a crystal, there is a different order parameter related to translation symmetry breaking. A condensate, Bose-Einstein condensate, has a third order parameter. And we know how to measure all of these order parameters. That's really the big advantage. That if you have an ordered state, there's a very clear-cut experimental technique usually that you can apply to tease out the order. So X-ray crystallography, again, known for almost a century, you can figure out which symmetry group, how your crystal breaks the symmetries of space, the translation symmetry, the rotational symmetry, and so on. Then we also have, for example, this beautiful image from 96, 95, Bose-Einstein condensation. You measure the condensate, the symmetry breaking condensate. Okay, so once you have this order parameter, you can measure it. You can also use it to classify all the different states of matter that you can get within this framework. So for example, for crystals, you find that there are 230 space groups. Of course, I'm ignoring quasi-crystals, which we know is also possible, but the original classification of regular crystalline groups, there are 230 of them. You can classify that. And what we have found over the years is, in fact, nature realizes each and every one of these space groups. You've gotten so good at figuring out if a crystal has a particular space group. Ultimately, it's kind of the principle that anything that's not forbidden is actually realized. Okay, so that kind of gives me hope that as we go ahead and we kind of predict and think about new states of matter, it's hiding somewhere in nature, and we should be optimistic about trying to find it. Okay, also, many practical applications of this Landau theory. You'll see many different phase diagrams like this one down here. As you change to thermodynamic parameters, how the different phases, the phase diagram, how it changes, and you can really understand that from simple calculations once you absorb the conceptual framework of Landau theory. And again, for more exotic phases of matter that we're going to talk about, the question is, are there practical applications? Okay, and so that is supposed to be an example which all of us can agree is important. It's a phase diagram of chocolate, I think. So there's no doubt that applying condensed matter physics or Landau theory to that is a major service to humanity. Okay. But there's one thing that's a little bit maybe kind of a bit disappointing about this whole Landau paradigm of ordered states, which is, although you're taking constituents, for example, it could be the spin of the electron, it could be the electrons themselves, the order, and ultimately the low energy physics is really described by this order parameter, which is essentially classical. If you think of a Bose-Einstein condensate, all the atoms condense into a single state, and that state becomes essentially like a classical state that takes on a life of its own. So it's you might have hoped that you have all this wonderful, interesting physics associated with the quantum mechanics of one electron or a few atoms. You would hope that when you put many of them together, you could end up getting physics that's entirely non-classical. Yeah, and in fact that is possible, but all of these states described by classical order parameters ultimately, not in a quantitative sense, but in some qualitative sense, they have a classical description. And it even applies to states that we normally think of as being quite exotic. So for example, superfluid helium, Bose-Einstein condensate I mentioned, shows these amazing properties, to creep up the sides of a vessel, and so on, all the amazing properties of superfluids. Essentially, you can think of that as the physics of classical waves. Okay, once you digest the fact that you should think about helium in terms of a wave function or a wave description, the subsequent discussion is all in terms of a classical theory of that, condensate or that classical wave. Okay, so we're really after states of matter that retain something non-trivially quantum, okay, not just at a quantitative level, but maybe also at some qualitative level. Okay, so we want to move away from this order parameter paradigm. So there are a couple of directions that you can go in that people have gone in the last few decades. So what if you have to distinguish states of matter that are not distinguished on the basis of symmetry? Are there examples like that? And we do have such examples, and probably the best known one, it came up in 1980, was the discovery of the integer quantum Hall effect. Okay, you have these beautiful quantized plateaus that you obtained when you measured the Hall effect, that first discovered by von Klitzing. And of course, the integers are discrete. So these correspond to states of matter, and you have a phase transition, go to a different state of matter. And the distinction between them is not on the basis of symmetry. They all have the same symmetry. It's really a topological distinction. It was later understood the discreteness of integers reflects that. And this discreteness, which is reflected in the quantization, how accurately you hit an integer, it's extremely accurate. Okay? In fact, it's the basis of some standards now. There are generalizations of these kind of states, topological insulators are more recent generalizations, but essentially it's this physics of the integer quantum Hall state that electrons, which are quantum mechanical, can display an effect which has no classical analog. Okay, there's a different kind of topological phases, which I don't know if I'll have the time to make a very clear-cut conceptual distinction, which goes under the name of topological order. And again, the most famous example are the fractional quantum Hall states, which was discovered a couple of years after the integer quantum Hall states, but conceptually they have many new elements in them. There are other postulated states of this kind, topological order, which we call gapped spin liquids. There's been a lot of work on that, and I'll come back to that in the second half of my talk. So these are two ways in which we could try to go beyond the essentially classical order parameter description, and find something new or potentially interesting. Okay, so first let me talk about the physics on the left, the idea of these topological phases that are similar to the integer quantum Hall effect, but we'd like to go a little bit beyond that. So the one step that you could add to that is, what if you combine spontaneous symmetry breaking with the topology of the integer quantum Hall effect? Okay, so that combination will give you something interesting. It has the physics of, has the topology of the quantum Hall effect in it, but it also has some interaction effects that lead to spontaneous symmetry breaking. Okay, so that'll be the first part of my talk. I'll talk about combining band topology with symmetry breaking or lambda order parameters. And this will actually make a connection with the previous talk in the series, which was given by Pablo from MIT about the twisted bilayer graphene. Okay, so although I'll be talking about twisted bilayer graphene, the way I want to think about this part of the talk is really as the first step to go beyond the order parameter paradigm, combining some sort of band topology with symmetry breaking. Okay, and this was done with my collaborators at Harvard, Islam Khalaf, who's a postdoc there, and my collaborators at Berkeley, Nick, Mike, and Shubayu. Okay, so I'll tell you a little bit about this work, and it'll be a bit sketchy, of course, but thankfully Pablo has talked to you before about this. Okay, but first I'll start with a simpler problem, which is just, what if you had the integer quantum Hall effect? This is what we had, right? This is what von Klitzing discovered in 1980. And the explanation was rather simple. There are things related to disorder that people had to sort out. essentially electrons in a magnetic field. That's what von Klitzing did. Very clean sample of electrons in a magnetic field. You get Landau levels. Landau levels are completely flat. You completely fill a Landau level and you end up getting one of these integer quantized states. Okay, that was the explanation that people came up with, and then they addressed it with more complicated issues. Now, of course, we all know the electron has a spin. So in fact, the more accurate picture of this thing is you have Landau level for spin up and spin down. They're slightly split in the magnetic field because of the Zeeman effect, but that splitting is often very small. So in fact, the true reason why you get, for example, n equal to 1 is that there is symmetry breaking. There is spontaneous symmetry breaking. The electrons spontaneously pick a spin direction, let's say up, fill up that particular Landau level, and they do not fill the down Landau level. Okay, and there is an energy gap, exchange energy gap, if you like, of delta that separates these two bands. Okay, so really this integer quantum Hall effect in the limit of small Zeeman fields. People have ways to tune the G factor of semiconductors, so essentially can switch off the explicit symmetry breaking. It's really a symmetry broken state inside a Landau level or inside a topological band. Does anything interesting happen in this particular case? Okay, and it turns out there's something very interesting that does happen. And it turns out that if you ask the following question, I have this filled set of Landau levels. I want to add one electron. Okay, I want to add charge to my system. And how does the electric charge go in? Okay, and it turns out that the obvious answer, which anyone might guess, is just put an electron into these empty levels. Okay, like you were filling the shells of an atom. It turns out that that's possible. So that would give you an electron which has one spin down in a sea of spin-ups. But it turns out that's not what the system actually wants to do. It turns out there's a different way in which the electric charge can enter. And the way it enters is in the form of skyrmions. Okay, so it forms a texture that looks like this. The spin is up very far away. At the center, it's down. And it kind of smoothly rotates from down to up as you go away from the center. And if you make this kind of texture of spin, it turns out it carries an electric charge. And you can convince yourself of that by figuring out that the electrons see a Berry's phase coming from the rotating spin. The Berry's phase is very much like a magnetic field. And in the quantum Hall effect, there is sort of an association between electric charge and magnetic field. So each of these levels over here, each of these states inside the Landau level correspond to one quantum of the magnetic flux. Okay, so there's this beautiful connection between Berry's phase of spin, the fact that there's a connection between flux and charge in the quantum Hall effect that gives you electric charge to this topological texture. And this is sort of in some limit. If you make the skyrmion very small, it ends up looking like just a single electron being put into this level. Okay, so ultimately you can change the size of the skyrmion. You can interpolate between these two limits. But this has some very clear experimental consequences. And people have seen that in experiments. They add one electron and they don't see one spin flip. They see many spins flip, like you would expect from this kind of a skyrmion. Okay, so that's kind of a beautiful consequence of combining symmetry breaking and topology. Okay, so maybe I'll pause here if there are any urgent questions.
Sorry, just to understand, what keeps this configuration stable?
Yeah, that's a good question. So there are competing effects. So one effect, of course, is the spin stiffness. So when you have a configuration like this, you're going to pay certain energy because of the spin stiffness. That stiffness doesn't really care about the size of the skyrmion. And in the usual quantum Hall effect, the competition is really between the Zeeman field. So there's a tiny Zeeman field, which does not like so many spins being overturned. You pay an energy cost there. But on the other hand, you gain because of the Coulomb interaction. Okay, so there's a charge density associated with this texture. The bigger you make the texture, the smaller energy cost you pay for the Coulomb interaction. So it's a balance between the Coulomb interaction and the Zeeman and the cost from the Zeeman field, and that gives you some size.
Since you have here a spontaneous symmetry breaking, you can write down some Landau-Ginzburg theory for this and find the skyrmion as a solution as a classical solution to this equation of motion of this theory?
Yes, that's exactly what people did. That's right. Yeah. And you can also show that that Landau-Ginzburg theory is slightly different from the ones we've been talking about before, because it has a topological term. Okay, so it's a topological sigma model, if you like, and I'll come back to that later when I, talk about a different application of this. Yeah, that's a great question. Thanks. Yeah, so just to elaborate one more thing, the energy of this configuration turns out to be somewhere inside this gap. Okay, so that's why it turns out to be more favorable to make this excitation rather than just putting in an electron. All right, so that is the situation in the context of quantum Hall ferromagnets. Now, what does this have to do with twisted bilayer graphene and what you heard from Pablo last time? So we believe, so it's a small group of people, we believe such physics is also relevant to explaining superconductivity and twisted bilayer graphene. Okay, I'll try to walk through the reasoning behind that in the next few slides. Yeah, so before I get there, let me make one conceptual point, which I think this sort of example really brings home. Normally we think of a ferromagnet, you think of electrons giving rise to the ferromagnet. Okay, so the fundamental degree of freedom is your electron. In condensed matter physics, that's our fundamental particle. And then there is a state where all the spins of the electrons align and you get the ferromagnet. So there's very clear kind of notion of what is fundamental and what is derived. That's our usual thinking. Okay, but in this particular case, you can actually invert that relation. You can, if you like, think of the spin of the ferromagnet as being fundamental. So like it was just said now, you can think of Landau-Ginzburg order parameter, Landau order parameter, a vector order parameter. That you can think of that as being fundamental. And then in that, you can make a texture, you can make a skyrmion, and you can convince yourself all the properties of that texture are what you would expect from electrons. Okay, so you can kind of invert this notion of what is the fundamental field and what is the derived field. And that's really because of the topological nature of the sigma model. And this has its roots in very famous work from Tony Skirm. He wrote down a theory, a quantum field theory for mesons, and showed that there are solitons of that, which are actually interpreted as the baryons, the protons and the neutrons, which is kind of sort of an inversion of, there's something surprising about that hierarchy of that construction. And, this was this famous paper from 1962. I saw this picture and I thought, he has a really nice Zoom background, but he passed away many decades back, and of course that's just 2020 doing these things to us. But this paper actually is kind of interesting because it turns out Tony Skirm had a very interesting life. So he was in the UK, and then he decided to move. And in this paper, he's got this little footnote. Where he says that he's moving to the University of Malaysia, essentially, right? Moving to Kuala Lumpur, and he lived there for a while. And another thing I found interesting in this paper is he has an acknowledgement at the end about a very bright, about a bright young student who helped him, carrying out these calculations. And I guess there's a misspelling there. That must be Tony Leggett. Who carried out these calculations while a vacation student that is at the place that he was working in. It's just kind of like a defense lab, I think. So anyway, that should give you, be a bit more careful reading applications for students applying for summer projects. You could get Tony Leggett or someone like that. So anyway, this was sort of the genesis of this kind of a topological sigma model. And now let me turn to how we think it has some connection to magic angle graphene. So I don't need to introduce this to you again. Two sheets of graphene that for reasons that are not very clear, people have thought about the idea of twisting them relative to one another. You get a moire pattern, so you get a lattice on top of a lattice. And the angles we'll be interested in are rather small. Okay, so the effective lattice that you get is, an order of magnitude or 2 orders of magnitude bigger than the atomic scale. Okay, and all of the physics that the experimentalists have been doing in this wonderful system has been to try to, add electrons or deplete electrons from this very diffuse and large lattice. It's like small dusting of electrons that are being added or removed, and you want to look at what happens quantum mechanically. And this particular angle is chosen because it's kind of a sweet spot where there's the time it takes for electrons to move between these lattice sites is roughly the same as the time it takes to tunnel from one layer to the next. Okay, there's kind of a resonance condition set up, and if you solve this particular problem, you find that at this particular angle there are extremely flat bands. Okay, so I showed you these bands that were like Landau levels, completely flat. This is the next best thing. Okay, they really look extremely flat bands, and the density of electrons over here, we're really talking about the small density corresponding to this lattice. And so there were these remarkable experiments from Pablo's group, Pablo, and this is Yuan Cao, who's a graduate student involved in that. And what they showed, this is taken from a different group, just has a clearer picture, I thought. As they change the density of electrons that fill up or deplete this little band over here, there are 2 copies of it for the 2 values of graphene. If that's not familiar, don't worry about it. It's just like spin. So there are flavors, valley and spin flavor that the electron comes with in this material. And as you fill or empty it, you get either this red, which is insulating states, or you get this light blue. That's the bottom of this color plot over here, which is very low resistance, essentially a superconductor. And we're going to try to explain this superconductor. And within our theory, which of course is fairly new, the way we think about this is that there is some kind of a topological sigma model. The sigma model, when it orders, it ends up giving you these insulators. But then when you add charge, when you dope it, move away from these integers, the charge goes in as textures, just like the ones we saw before fermions. And that can end up giving you pairing and a superconductor. Okay, so I'll try to describe that very briefly in a few minutes. Okay, so why would this quantum Hall physics that we talked about, electrons in a very strong magnetic field, Landau levels, etc., why would that have anything to do with this material, which has no magnetic field present? It turns out there's something remarkable about these very flat bands that we saw, in that they have a certain character to them that allows you to apply quantum Hall physics. Okay, of course, you've not broken time reversal symmetry, but you can split up this band into 2 pieces. One of them that looks like a Landau level with magnetic field pointing up, and another one Landau level with the magnetic field pointing down. Okay, so that's, just take my word for it, that's what these flat bands, you can decompose them like that. And because the kinetic energy is very small, these really feel a lot like Landau levels. Okay, they have the same character, they have very little dispersion. And it turns out that for simplicity, I'm ignoring the spin of the electron. You still have 2 flavors, okay, depending on which of these 2 valleys your electron comes from. Okay, so it really looks like you have to fill 2 out of these 4 bands, very much like what we had to do in the quantum Hall effect, the quantum Hall ferromagnet. Okay, so except that things are doubled over here. You have both magnetic field up and magnetic field down. Okay, and the fact that you have this doubling gives you the possibility of superconductivity, okay, which you don't have in the usual quantum Hall ferromagnet. Okay, so that's roughly the connection. Again, I just have to cut to the punchline in this, given the limited time, but hopefully this will make the basic idea clear. You can get skyrmions. So again, the charge can go in as skyrmions because you have these 2 different labels. And in fact, there's a regime where we believe the charge does enter as skyrmions. But now there are 2 sectors. There's a magnetic field up, magnetic field down. And it turns out that the 2 sectors, the skyrmion, the direction of this ferromagnetism, the direction of the vector, locks in an antiferromagnetic way. Okay, so if it is up over here, it is down on the opposite side. So the net result of all of this, if you step back a little bit, It turns out that it's possible that the lowest energy charge excitation is actually a charge 2 object. Okay, so each of these has charge 1. They are bound together, which is what we expect for Cooper pairs. Okay, and you can also convince yourself that these Cooper pairs have inertia. They can condense. They have an effective mass. And the calculation is very similar to how you think of a vortex ring, these smoke rings. The dynamics of smoke rings is very much related to how this object receives an inertia. Okay, it's like an attraction between particles that are experiencing opposite magnetic field. So again, let me skip through that, but let me just point out one thing that was asked before, that this is a sigma model which has a topological term. Okay, so I've rewritten the sigma model in terms of what is known as a CP1 representation. It's some equivalent representation which you replace the vector of the sigma model by a pair of complex fields, and you end up finding that it's very natural to write this in terms of a gauge field. And this gauge field has nothing to do with the external electromagnetic field. It's an emergent gauge field. And this gauge field is really keeping track of the fermion density. Okay, so when there's a
sorry, I got confused. To begin with, you had a gauge symmetry. Forget about the photon, a gauge symmetry.
You have electrons, is that what you mean?
Well, I don't know. If you can write down in terms of some effective theory all of this again, then in whatever, and you can write down whatever effective theory, effective Hamiltonian, whatever you want. Does this theory have a gauge symmetry?
Yeah. So the gauge symmetry
because
is
I mean, okay, you realized here the gauge symmetry one way, but you had gauge symmetry probably to begin with.
You had a different. So gauge symmetry is a bit of a tricky thing. Because,
gauge symmetry, I mean some symmetry under.
Can we let the speaker answer, please?
Yeah, let me say one or two sentences and we can get back to this at the end. So by gauge symmetry, I think you mean, to me, what it means is really this emergent gauge field, little a, right? And what this gauge, usually we think of gauge symmetry as something being conserved, like electric charge being conserved. Here that corresponds to this, keeping the length of this vector fixed. That's technically how this gauge field appears. But we can have a longer discussion about this. In my view, this gauge symmetry, unless you have a deconfined phase, the gauge symmetry is not really it's partly what your way of keeping track of variables. And there are different ways of describing the same physics. It's kind of non-negotiable when you have a deconfined field. We'll come back to that in the next example. But this I think is an interesting point to discuss further, and it's a slightly different way in which you're brought up to think about gauge symmetry in particle physics versus in more of an effective field theory. Yeah, but CP1 representation of the sigma model is very well known, right? You can find it in Polyakov's textbook, and that's all I'm doing over here.
CP1 has to begin with gauge symmetry.
It's just a rewriting of the sigma model.
I mean, at this point, your gauge field is just an auxiliary. I can integrate it out.
Yes. If you wish, you can. That's right.
You don't have yet the F squared term in my language.
Yes, but if you do a renormalization group, you think of integrating out high energy modes, you will generate an F squared term. Right? In the Wilsonian picture, in the effective field theory, you will have an F squared term.
Yeah, you generate it, but because you had the gauge symmetry to begin with. It's
yes,
not
but
the global symmetry, and you integrate something, and you get a gauge, and you get a gauge field.
Let's get back to this because I think I have a better example where you can have the same discussion and everything is a lot clearer. This is all in the continuum. It's not very easy to discuss, but let's get back to that. But okay, so within this description, there are two phases, whether this field is condensed or not. And within our picture, those correspond to the two phases of that are seen in experiment. We think, this is the way to explain them, the insulator and the superconductor. Okay, so you can also calculate things like TC for this superconductor and so on, and it matches reasonably well with the experiment. Of course, that's not a proof, but the real question is, can you actually predict other materials or other setups where the same theory would apply and have a reasonable chance of showing the physics that was seen in magic angle graphene? And it turns out that you can do that. Yeah, so I actually skipped this part. There is some evidence from DMRG that this picture is energetically reasonable. It's still not, we still don't know the microscopic parameters well enough to be completely sure, but it's not a crazy idea. Okay, the parameters of graphene are within the range where this kind of picture could apply. But one thing it tells you, this mechanism, is that there's a certain symmetry in this problem that's extremely important. Okay, and that symmetry is a rotation, 180-degree rotation followed by time reversal symmetry. Okay, and if this mechanism is to apply to some other platform, it had better have the same symmetry. People have made all kinds of different sandwiches made up of graphene and other materials. And this magic angle graphene that Pablo first pioneered, that has the symmetry, of course. Okay, that's how this theory came about. But it turns out there are very few other systems that actually have that symmetry. Okay, so you can rule out a lot of phase space, at least for this theory, and you can try to see, is there anything left? And there is one that is left behind, and that corresponds to this tri-layer graphene. Okay, so this actually came out of work within my group, that if you take alternating twist tri-layers, so you take a layer of graphene, twist, and then twist back, you can kind of decompose this into something that looks like bilayer graphene and an additional layer, okay, that kind of coexist. And this bilayer graphene, of course, has the requisite symmetry, or this whole sandwich has the requisite symmetry. And we believe that the same physics would appear over here, except everything would be increased by a factor of square root of 2. Okay, so it turns out you do the mapping, you get a magic angle that's somewhat bigger, 1.55 degrees rather than 1.1 degrees. This makes everything a bit more robust because the interactions are stronger and energy scales are bigger. Okay, so we of course talked to some of our colleagues who work in this area, and we were not very optimistic that we would be listened to, because there's a long tradition in condensed matter physics, especially superconductivity research, when theorists predict superconductors, right? And it's kind of codified in these rules. These rules that Bernd Matthias came up with in the 1980s for looking for superconductors. This is he passed away in 1980, so this was before IPC was discovered. So a lot of his rules actually are violated by the cuprate superconductors. In fact, stay away from oxygen and stay away from magnetism, stay away from insulators. All of those were violated. But there's one golden rule that was not violated, right? Which is rule number 6. Don't listen to theorists. So there's kind of a culture in the field that you don't listen to theorists. And but luckily, I think the people we talked to were a bit didn't know about these rules, right? So they went ahead and they really looked into this in great detail. And there was this beautiful paper again by Pablo's group, who looked at this. They call it mirror symmetric tri-layer graphene. It's really this alternating twist. They looked at this angle, this square root 2 times the original magic angle, and indeed they find superconductivity in the system, and it can be tuned with electric fields and things like that. And we are still trying to digest this, the physics that come out. And just today there was close behind there was this paper from Philip Kim's group where also sees very similar kind of physics. And one of the interesting things in this problem, in addition to magic angle flat bands, there are also these highly dispersive Dirac bands. So we think that's it doesn't change the physics in a huge way, but again, it's something that is an open question at this point. Okay, so so in the remaining 10 minutes, I think I have 10 minutes left, Daniel. Yeah, so let me tell you, slightly switch gears. And tell you about the second column that I had in this exotic states, which was to talk about phases which have topological order, so a different kind of topology from the quantum Hall effect or what we saw before. So this was again worked on it with my in my group with Ruben Verison at Harvard and with Misha Lukin, who is an expert on the platform that I'll tell you about in a second. But the background over here is, one of the best examples of this kind of topological order is the fractional quantum Hall effect. And despite appearances, it looks a lot like these quantized plateaus. This is the famous 1/3 Laughlin state. This is, it has a new feature, which is emergent excitations, which are anyons. Okay, they're neither bosons nor fermions. They have statistics, they characterize these kind of topological orders. There's a different family, which is called the spin liquids. So even without a magnetic field, just in a piece of rock, basically in a material, you can pick it up, and the hope is under certain conditions, you will also realize such, something similar excitations that have no analog just in terms of bosons or fermions. And there are many questions here that we wish we had something like an order parameter to address. How do you measure? How do you classify it? How do you realize it? It could be more common than you think. We're just not very good at teasing out these signatures, okay? So there are many examples that people have tried to look at experimentally for quantum spin liquids. These are three of the most promising candidates. They may all be spin liquids, we don't know. But a very precise characterization of them has not appeared yet. In particular, of a gapped spin liquid. That's really the closest analog of these fractional quantum Hall states. There's an energy gap, and then you have these exotic excitations. Okay, so there's a big open question. How do you realize these types of states of matter? Okay, without a magnetic field, without going to extreme conditions, like the quantum Hall effect, can you realize topological order? Okay, so we have some proposal to do this, but let me just tell you a little bit of the history. So the idea that quantum spins could form this goes back to Anderson and almost 50 years ago. So he thought about magnets that are frustrated. So things like this is called a Kagame lattice. You can't quite orient the spins in a way that will satisfy an antiferromagnetic interaction, okay, where the spins want to be antiparallel. And then you could imagine other states take over. This is an example where pairs of spins form singlets, and then they arrange the singlets in some way, and then they quantum fluctuate. So, Anderson had this intuition that it could, quantum fluctuations could melt this picture. You have a superposition of all different kinds of combinations, give you a liquid-like state of he called these valence bonds, a valence bond liquid, a resonating valence bond liquid. And in the decades since, we have come to understand this, the correct way of describing this in, within quantum field theory kind of language is in terms of an emergent gauge theory. Okay, so maybe this goes back to the old question. Here you have these dimers, essentially these things that live on the bonds, and you can think of them as satisfying a Gauss law constraint. Okay, this is like an electric field, and you don't care where the electric field is on this set of 4 sites. There has to be one of them coming out to take care of the spinner half, the spin over here making a singlet with one of its neighbors. Okay, so you can think of this as an electric field and the divergence of the electric field being 1. Okay, it's being something fixed because there's a charge on every side. And then when you think of quantum fluctuation of these dimers, it's really quantum fluctuations of the electric field. And that is kind of an emergent electromagnetism that can arise in this model. Okay, that's kind of the deconfined phase of this gauge theory. There's an important caveat, which is really that this is a Z2 gauge theory. It's based on a discrete group rather than the familiar U1 group of electromagnetism or Yang-Mills kinds of theories, which have other continuous groups. And this is literally the simplest model of a gauge theory that you could think of. The question is it in a deconfined phase? And this description is completely trivial in a sense, because any configuration like this you can describe in terms of electric fields. That's why I said that this gauge theory is not, just saying it's a gauge theory does not mean much. But if it's in a deconfined phase, then exciting things happen. Okay, and that's really a physics statement about the longest scales of your problem. Okay, so in magnets, people have not quite been able to realize this. So we've been thinking about other ways to realize such a Z2 topological order, if you like, the Z2 the Z2 gauge theory. And this is kind of the physical platform we have come up with. Maybe this is it's going to get a bit complicated if you think about many of them, but the two-side problem, just two sides, instead of having atoms with spin, we have atoms that can be either in the ground state or excited into a highly excited state. So these are called Rydberg atoms. And this excitation into some highly excited state gives you an interaction that is hard to combine with regular spins or regular solid state systems. Okay, so this is completely synthetic system. Atoms are trapped in some optical tweezers. They're like, order of microns apart. And you have a qubit. You have a two-level system on each side, ground state or highly excited state. And people have made arrays of them, especially in this Lukin group, arrays that can reach up to 50, 100, 200 of these. And they have the following simple Hamiltonian. There's a single site Hamiltonian. You can cycle between grounded and excited state, or you can have a splitting between them. Okay, that has to do with detuning. There's a single site Hamiltonian that's quite general. But in addition, there is interactions. Okay, and that's what's really important in this thing. The interaction takes the form of what's called blockade. So if you excite one atom over here, because it's this giant orbit, it kind of prevents you from exciting any of the atoms within a certain radius. And this turns out to be very good for us to get the kinds of models that we are interested in. So we came up with a lattice, atoms on a particular lattice that it's some funny lattice. It's called the Ruby lattice. It's on the links of a Kagame lattice. So there's a blockade radius that is carefully chosen like this, and very simple Hamiltonian, just a two-term Hamiltonian that approximates the system. And okay, so I'm almost out of time, so let me just show you the phase diagram. We get a phase where, as you vary these parameters, the detuning versus the cycling time, the Rabi frequency, you go from a trivial phase where nothing interesting is happening. On the other extreme, you get some kind of a solid. So I showed you there's a picture where atoms are sitting at certain points, or the valence bonds were just occupying certain of these bonds. These are the two uninteresting phases. Okay, but in between, you find a liquid phase, which has all of the properties of a deconfined Z2 gauge theory. Okay, and it's called a spin liquid, but there's a very nice way to identify it in terms of topological entanglement entropy. I couldn't introduce this, but essentially the fact that it goes to this number of -log2 tells you that this is very likely candidate for a deconfined phase of a gauge theory. Okay, so what is this good for? That's the last question we had in that list. And there's a beautiful proposal by Alexei Kitaev that has really sustained this field, which is that this may be a way to encode quantum information in a way that is not susceptible to decoherence. Okay, you know that quantum bits are very susceptible to interacting with the environment, and the careful superposition you make them in is destroyed by that decoherence, right? But if you instead encode the quantum bit not as a single bit, but in terms of these many bits, so I've shown a torus because that's the origin of this word toric code. You get a degeneracy of the ground state corresponding to different sectors or Wilson loops of this gauge theory. And for example, this particular arrangement would give you 2 quantum bits encoded by many physical quantum bits. There are 2 protected bits, and maybe that is a way to protect quantum information from the environment. I think most people believe now that some scheme of this kind, either by using ground states or actively doing error correction of this kind, is going to be necessary if you want to make large-scale quantum information processing device. Okay, so this of course, this is something we're very interested in, and you don't need to make it on a torus. Here are geometries that we could use for our lattices that we could use to access them. So the experiments have not been done yet, but we think the model is quite close to what can be done in future experiments, and hopefully we can come up with some design to try to make a quantum bit that is protected against decoherence. So that's kind of a baby step towards a more general fault-tolerant quantum information processing. Okay, so let me end over here. So the main thing I want to kind of convey in this talk is that all of these very amazing ideas like emergent gauge fields and topology, we didn't talk much about quantum entanglement, but that lies at the heart of all of this physics. You think of that as very exotic ingredients or very exotic outcomes. But the things that are going in are extremely mundane. In fact, this is a lump of coal. And if you look, people have been trying to use coal now to extract graphene. So you take this, graphene from coal, and of course you do it just right. It can't quite be like this. It's got to be properly stacked and so on. You get the amazing physics that Pablo was talking about. The second system I talked about, again, very simple system. It's just a bunch of atoms that can be in ground or excited state. Think about it, it's just light. It's just exciting these things. So it's kind of trapped this photon, de-exciting it, exchanging photons with this environment, with this laser, if you like. And if you design the interactions correctly, it can go into this phase which has all these amazing properties. So you don't have to look very far, or you don't have to look in very exotic settings, but the physics could be extremely exotic once you have many interacting quantum particles. Okay, so let me stop over here.
Thank you very much, Ashvin, for this very interesting talk. And so let's start. We have time for a few questions. Asa Arbach has a question.
Hi, Ashvin. Great talk. Thanks.
Hey, thanks.
I have a question about the superconductivity in twisted bilayer graphene.
Yeah.
How do you explain the phase diagram, the insulator and the superconductors as a function of density with your picture?
Yeah, good. Let me go back to that. I think this may be a good one. Forget about the y-axis over here. Let me just repeat. You know this, of course, but let me just repeat it so people know what the question is. So what you see over here in this resistivity trace, for example, you have these insulators, and in between you have the superconductor, right, over here and over here. So our theory is built, really for this particular, keeping this particular insulator in mind. So it's beautiful work from the Weizmann Institute where they showed that there's flavor polarization. So you can kind of throw away the spin when you get an e equal to -2. And the sigma model we develop is really for, the generalized ferromagnet, if you like, generalized quantum Hall ferromagnet in the vicinity of this particular filling. And when that sigma model is ordered, that's the insulating phase. But when that sigma model fluctuates, the skyrmions of that sigma model are actually electrically charged. So although, usually when you write down a sigma model for flavor ordering or for spin ordering, you throw away the charge. You don't know about the charge degree of freedom. But here, because of this band topology, your sigma model actually keeps track of the electric charge. So just by looking at the phases of the sigma model, you can tell whether you're an insulator or a superconductor. And that's roughly what this calculation was attempting to do. So we did sort of a large end treatment of this topological sigma model, where you add in, essentially what you do is you change the chemical potential on the sigma model. And what that does is it forces in skyrmions, because the skyrmions, of course, where the charge density is living. And once you have a finite density of skyrmions, you cannot sustain the order in the sigma model anymore. You lose the order. And in that phase, you get a photon because there's no Higgs phenomenon anymore. You get a gapless photon. And by duality, that gapless photon is just the superfluid mode of the, if you're a neutral superconductor, you'd have a gapless mode. And that's really what this is showing, that as you crank up the chemical potential, there's some coupling over here, G. We are somewhere here at small coupling. You have a gap. So you have to have a finite chemical potential. You have to raise it. And then beyond a certain point, the skyrmions come in and they form a superfluid. And you can calculate the superfluid stiffness just by integrating out all those degrees of freedom and finding the F squared term, like it was said before, the Maxwell term for little a, the coefficient of the Maxwell term is actually the superfluid stiffness.
So you need to be off the integer filling, right? You have to.
You need to be off. I mean, in principle, you could imagine tuning interactions so that you could stay at integer filling and quantum disordering the sigma model. But in reality, that's very hard to do because of strong repulsive interactions, right? But within this theory, in principle, you could get a direct transition into a superfluid as you lower the value of G, the coupling constant of the sigma model. But in practice, that's very hard to do. It's much easier to just dope it and go into a superfluid.
And how far can it hold away from the integer filling? I mean, the superconductor.
That's a very good question. We don't know. This theory doesn't give you a sense of that. But I would guess that when the filling is of, this is like an effective low energy theory. So you've integrated out things on the scale of the Moiré lattice. So once the charge density becomes a sizable fraction of the Moiré lattice, scale, it should not really work. So, sometimes, of course, things work beyond where they're strictly supposed to work. But if you look at this phase diagram, actually, this is a beautiful, from our point of view, this looks really beautiful because we'd expect a linear rise of TC with doping. Simply add more carriers and they all contribute to the superfluid stiffness. In fact, we can more or less predict the slope. We can't predict exactly, but within a factor of 2, the slope works out. But then you get to like about 50% filling, and then I don't think our theory can apply anymore. And then things fall back down.
So if you want to check the theory, would you put a magnetic field to destroy your mechanism?
That would work. So if you put on a magnetic field, this kind of coupling between the different churn sectors, I don't know if I had it. There is this kind of coupling. This will be destroyed.
Okay.
But again, it's a question. It's much easier to compare one theory with another one, rather than try to prove a theory just by itself, right? So if there's another, there are actually not many strong coupling theories for this problem. This one thing we really like to do is to put in all the realistic features of bilayer graphene and numerically simulate and see if this is what happens. And initial signs are quite good. That if you throw out some of the details, use lambda levels instead of actual bands of bilayer graphene, there is a regime where you get skyrmions and you're on the borderline for magic angle graphene. You're on the border of where that's working. So maybe some truth to it. Maybe not literally true, but something about it is capturing the physics. But we have to wait and see.
Okay, thank you very much.
Okay, so we have a few more questions, but I suggest we first, given the time, I suggest we first thank Ashvin, and then whoever wants to stay with questions, please stay. And
can I make a question?
Yeah, but first, no, there's an order. There's 2 people before you. So
right.
There's Yigal Meir. Yigal? Okay. Yigal, are you there? Okay, well, let's try first Jonathan Ruman and then Yigal if somehow we cannot hear you.
Hi. So I would like to continue the question by Asa on superconductivity. So just to understand, what binds these 2 skyrmions is the emergent gauge field, which presumably...
No, sorry. That's a good question. And unfortunately, I skipped over that. So there's an all-important coupling J over here that binds the skyrmions together. And you can ask, what is the origin of that?
Yes.
So let me go back one step. So I told you that this is the setup. We have to fill 2 out of these 4 guys. And there are different ways of doing it, but some ways are preferred compared to others. So for example, let's say I fill this one over here, and I fill, let's say, this one there. So it turns out this is a preferred arrangement because you can do a virtual process. So you can tunnel over here and tunnel back. And it turns out the coupling that connects these two sides is actually the kinetic energy. It's small, but it's there. So the kinetic energy hops you there and then hops you back. And there is some repulsion cost that you pay when you do this. So it's very much like super exchange in the in oxides or something. There's an effective J, which is T squared over U. Again, U is some Coulomb scale, T is the kinetic energy. That would like to bind the vectors in the opposite charge sectors antiferromagnetically. That is the origin of that J.
So presumably this overcomes the Coulomb interaction?
That is kind of the picture, that the Coulomb interaction is reduced because these could be relatively big, or at least somewhat reduced. And then J, if you go to the limit of just a single skyrmion with no anisotropy at all, this J always wins because it increases with the area, whereas the Coulomb is dropping once you go to large scales.
I see.
Yeah, but that is intuitively what we have in mind. Of course, that's very classical way of thinking about it. So in the numerics, when you put in these ingredients, you get a superconductor, basically.
I see. But do you expect to see preformed pairs and this physics of BC?
Yeah, that's, if you take this picture literally, that's what you would expect. Now, of course, you could have dressed versions of this, and in fact, that may be realistic. That we're trying to say this charge 2 object is the lowest charge excitation, but you could have electrons which have some dispersion, and one point in the Brillouin zone, they could have a lower energy. So now when you start filling up charge, you don't actually start with the skyrmions, you start with electrons, but very quickly the Fermi pressure will end up being large enough that the skyrmions become competitive. So you could have variants of this, but in the simplest picture where you say this is the lowest energy charge excitation, yes, it is more like BEC than BCS.
Okay, thanks.
Okay, so next Yigal and then Ribeiro.
Okay, do you hear me now?
Yeah.
Yeah.
Okay, thanks for the talk. I have a very simple question. You made a distinction between integer and fractional quantum Hall effect. I kind of grew up believing that the fractional quantum Hall effect is just an integer effect for composite fermions. So, and there's no difference between the physics of the two effects. Is that something that I should now disbelieve?
I would agree with everything you said, except the word just. You said it's just the integer quantum Hall effect for composite fermions. It is true that it is the integer quantum Hall effect for composite fermions, but that is a substantial leap. When you talk about putting an exotic particle like the composite fermion in an integer quantum Hall state, that leads to all kinds of consequences. And the amazing breakthrough in the quantum Hall effect was this complicated physics, that actually is associated with the fractional quantum Hall effect, which is different from the integer quantum Hall effect. All of that can be somehow, packaged into this idea that composite fermions are forming integer quantum Hall states. So one very clear-cut distinction between the two, integer and fractional, is if you look at the excitations in the integer quantum Hall effect, you have a ground state, you have a gap, you have some excitations. They're essentially electrons. They could be dressed or something like that, but essentially, at the end of the day, they're electrons. They carry the charge of the electron, statistics, etc. Fractional quantum Hall effect, as you know very well, that's not true. The excitations are anyons, and that leads to all kinds of consequences. There are further, there are these non-abelian anyons as well, and more and more complicated versions of this. If you want to, for example, make a protected quantum memory, the kind we talked about, the integer quantum Hall effect is not going to do it for you. You really need either the fractional quantum Hall effect, or you need to engineer things like superconductors, integer quantum Hall effect, stuff like that. So the actual, in terms of consequences, the physics, what you measure and stuff like that is quite different. But amazingly, there is this conceptual link.
So it all comes down to the wave function of the single composite fermion? Is that what causes all this complex structure or complex excitations?
The composite fermion itself is a deceivingly simple looking but very complex object. It looks like, oh, you just attach flux to electron, but that is a profound change, when you do that. And it's a non-local excitation. If you have a composite fermion here, you can go very far away and detect it, which you can't do with regular electrons. You take another electron far away, you can't tell there's an electron inside. I mean, maybe from the Coulomb interaction, but otherwise you can't really tell. So you're changing to non-local variables, I would say. Maybe it's related to your comment about wave function, but often this is what we're trying to do in any physics problem. There is some other set of variables where the physics is really simple. And the hope is that, and you're trying to find those variables. In some cases, you cannot do that and you're stuck. But yeah, when you can do that, it allows for a lot of progress. The same way the Z2 spin liquid I talked about, the similar way of thinking about that is you can think of it as a superconductor, except the charge is thrown away. So that's how Anderson thought about the Z2 spin liquid. It's actually a superconductor and you project out the electric charge. Now we know the physics of a magnet is very different from a superconductor, but in conceptual space, they may be related. And it's somewhat similar for composite fermions, I'd say.
Okay, thank you.
Okay, Ribeiro?
Oh, okay, Ashvin, thank you for this nice talk. My first question is about the topological sigma model. In your deconfined theory of criticality, I used to read about the nonlinear sigma model with a topological Hopf term. What is the difference?
So it turns out this particular sigma model I wrote down does not have a Hopf term. I mean, the Hopf term is just a mathematical way of keeping track of the statistics of the skyrmions. So in this particular case, it's like a Cooper pair, so it has only bosonic statistics. If you wrote down the sigma model for, or nonlinear sigma model for the quantum Hall ferromagnet that I talked about, this one here, right? This one does have, I didn't write it down, but this one has a Hopf term because the skyrmions are actually fermions, they're electrons. But there's a second topological term which I'm more interested in here, which is not so much the statistics, but the fact that they carry electric charge. And that was in this particular term over here, that the external electromagnetic field can couple to the flux of this. It's actually, you can write it in terms of the sigma model fields as well. This density over here is skyrmion density. It's n dot product dx and cross product dyn.
Okay, but I thought, right, but I thought that the Hopf term was an intrinsic ingredient of your theory, because in two dimension, the classification of the topological term is the Hopf term. Here, you are in a two-dimensional system, right?
Yes, that's right. This particular model does not have the Hopf term.
So, how do you classify your topological term?
Whether it carries electric charge or not. So there's another symmetry in the problem. It's not pure sigma model. So if you have a theory which has only the rotational symmetry of the sigma model, you cannot write this term. The reason you can write this term is there's an additional U1. The symmetry is not SO3, but it's some U1 times SO3. And this term links the U1 and the SO3. The target manifold of the sigma model has textures which carry symmetry charge under the U1. So it's kind of an extension. You need to extend the thinking of the usual topological sigma model a bit here to make it appropriate for electrons.
Ah, all right. My second question is about the phase diagram between the spinning liquid and the VBS phase. How do you classify that spinning liquid?
Yeah, that's a very good question. And we did about 5 different ways. I just showed you one. So one thing you can do is, actually I removed it from this, sorry. To make that distinction, it's kind of easy because you can just look at the density. So you can look at the density of excitations on the sites here and over here. And you see in this valence bond solid, there's a clear modulation of the density. Whereas over here, it's uniform. But it turns out there are 2 different uniform states. It can be uniform like this in the spin liquid, or it can be uniform in the trivial phase. And to make that distinction, you see there's a phase transition going from one to the other. This is the correlation length, it diverges, continuous phase transition.
Okay.
So you need another measure, which turns out to be this topological entanglement entropy.
Right.
And this number turns out to be minus log 2 in the spin liquid and 0 in the other phase.
Look, in some moment in the past in your works, you said that when you broke two different kind of symmetry, you have a deconfined quantum criticality, right?
Yes.
So
yeah,
this is the case here between the spin liquid and the VBS?
Not really. Yeah. So here it turns out this is just a first order transition.
Okay.
It just jumps into that. But the deconfined criticality story is actually relevant to the previous thing. I didn't talk much about it because I think it's not very relevant to the experiment and magic angle graphene. This was actually Asa's question. If you disorder the sigma model over here
Right.
spontaneously without doping, that transition would be from one of these ordered states, ordered insulators, into a superfluid.
Right.
And that is forbidden by Landau theory. They're two different ordered things. In fact, the theory we get over here is exactly the CPU1 without monopoles. Same theory we had there. But I didn't really talk about that because that requires changing the value of G. It's really this transition as you go up here. And in experiment, they cannot really do that. They can only go out like this. They can only dope it.
Right. Thank you.
Efrat?
Yeah, thank you for a great talk. So I have a question about the possibility of other topological excitations in the graphene bilayers. So can you have some kind of domain walls if you're considering edges or some kind of, basically,
yes.
Can you get a binding of domain walls that are also charged excitations that may even have lower energy?
So domain walls, I could imagine configurations where you have gapless modes on the domain walls,
right.
or at least approximately gapless.
Right.
So for example, simple one would be you fill both of these churn 1, and in some other place you fill both of these churn -1, and that boundary, as you know, will have gapless modes as long as they don't mix,
right.
But in terms of the domain walls carrying charge, yeah, that's sort of an extended object. So it may be tricky to define the charge, and you can define a charge density. But so you're thinking maybe when you add charge, it could go in the form of domain walls. Yeah, that could be, yes.
Right.
Yeah, that could be. That's a good point. You could have maybe like bubbles, kind of, where you have, actually the skyrmion, you can think of it kind of like that. If you have anisotropy, like it's not a very good picture of a skyrmion. Actually, I realized I didn't have a very good picture of a skyrmion. So if you look at this picture of a skyrmion, you have spin up in the center and spin down in the center, spin up at the boundary. If you squish the region in between where you have stuff just along the equator, that's kind of the domain wall between up and down. And that by continuity, it would carry electric charge. Of course, if it's that anisotropic, it may not be stable, but it may not be energetically favorable. But yeah, that's certainly a possibility. It still has some features that may be different from, just a single spin flip.
Okay, thank you.
Ashvin, I have a question about this, these Rydberg atoms and the Z2 spin liquid. Like, I know it hasn't been realized experimentally, but do you know, in principle, how would you control the excitations and drag them and all that? What would be the operation?
Yeah, that's a good question. So, we have a very specific thing in mind, which is we want to make this kind of a topological quantum bit. And of course, we can't put it on a torus. The idea is to put it on the plane and have different kind of boundary conditions. So you can label the boundary conditions by which anion is condensed at the boundary. You've got to condense either the E or the M anion at the boundary. If you make an E condensate everywhere or M condensate everywhere, there's no degeneracy. But if you do 2 of them E and 2 of them M, then you have a degeneracy or twofold degeneracy. So this is the quantum bit. And we've figured out ways of how to do this, at least in the model, numerical model, how to change the Hamiltonian on the boundary to get the 2 different condensates. And we can see the twofold kind of state over here. And then what you want to do is you want to take an anion and move it through. If you want to toggle the state of your quantum bit. And you can do that by, for example, you pick a site and you change the detuning, for example. You change one of the parameters of the Hamiltonian there. And it's kind of intuitive why it's an E particle. It's like, if you think about this model over here, when this detuning is large, it becomes a gauge theory without matter fields. If you lower the detuning, you can trap essentially a Z2 electric charge. And then you can change that as a function of position. You got to change the function of time and move it. And the experimentalists tell us that's, it's not trivial, but it's possible. And then you could do this. So it's not quite braiding yet, because this theory has nothing interesting in the braiding in that sense. It's a abelian theory. But this will allow you to toggle between the states of this qubit, if you can do both for E particle and M particle. And you can think of this, another way to think of this qubit is at the boundaries, at the corners over here, you have Majorana fermions. Of course, of this emergent fermion, right? And there are 4 of them, so you would expect 4-fold degeneracy, but you're in a fixed fermion parity sector, so you get a 2-fold degeneracy for this quantum bit. Yeah, so the first goal is just to make a quantum bit that is more robust than the individual bits, and to be able to toggle, measure it, toggle it, and stuff like that. But you could imagine, let's say you make a more exotic state, maybe you can take these excitations and braid them, or make a hole like this and braid it around, and then you can realize more exotic kinds of statistics.
Okay, thank you. Okay, well, are there any more questions? Well, if there aren't, let's thank Ashvin again for this great talk. And thank you.